Amines are bases, and so amines are going to react with acids to form salts. Here's a reaction shown that is an example of this. Here's trimethylamine with hydrochloric acid, and it forms a salt. Notice positive charge on the nitrogen because it now has 4 bonds, and then the chloride is its counter ion. The way that we name these is that we name the amine and then follow with the a modified name of the acid, so it's trimethylamine hydrochloride. So go ahead and you try it. Draw and name the product of aniline with hydrochloric acid. Okay, aniline has this structure, and there's hydrochloric acid. Of course, the proton from the hydrochloric acid adds to the nitrogen, and we get this salt. How do we name it? We're just going to name the base, aniline, and then follow it with hydrochloride. Amines also will react with carboxylic acids. When we were in the carboxylic acid derivative chapter, I tried to get across the idea that amines do not react with carboxylic acids to make amides, that what happens instead is there is an acid-base reaction. So you get a salt from the two. Now, students often get confused with this, and I think it's because in biochemistry and in biology, you're constantly being shown amines and carboxylic acids forming an amide in the peptide bond. And so you just naturally think it has to happen in organic chemistry too. But biomolecules have enzymes that help them do reactions, and organic chemists only have solutions. So reactions that chemists would find impossible to do, enzymes are able to do lickety-split. So keep that in mind, that amines and carboxylic acids react together to form a salt. You actually see that in the formation of the Zwitter ion in an amino acid, which we'll cover when we look at amino acids. When we're looking at amines, we describe their basicity according to the pKa of the conjugate acid. The conjugate acid, when stronger, means a weaker base. And when you have a weak conjugate acid, it's a strong base. So the larger the pKa of the conjugate acid, the stronger the base will be. So you can just look at the pKa, and the highest pKa of the conjugate acid gives you the strongest base. The lowest pKa, the most acidic conjugate acid, gives you the weakest base. So go ahead and apply this knowledge in rating the basicity of these three amines. Okay, when I look at this, I see pKa here is high, indicating a weak acid. pKa here is low, indicating a stronger acid. Because this is the stronger acid, this will be the weakest base. Since this is the weakest acid, this will be the strongest base. So 1, 2, 3. Go ahead and try it again. And now, since you've gotten this twice, trial on this twice, since this has conjugate acid is weakest, this will be your strongest base, and since this is your lowest pKa, or the strongest conjugate acid, that will be your weakest base. So this is the rating that you should get. Where does this basicity come from? It comes from the non-bonding pair and its characteristics. If the non-bonding pair is not available at all, as we see with amides, where the non-bonding pair is completely pulled into the pi system of the carbonyl, or the non-bonding pair in an aromatic ring, where it's completely pulled into the aromaticity, both of those non-bonding pairs are non-basic. Now, when we're looking at the non-bonding pair that's part of an aromatic ring, it must be a non-bonding pair that is counted in the 4n plus 2 electrons. If it's just a nitrogen that is in an aromatic ring, but it has a double bond to it, that non-bonding pair is not in the aromatic system, so it's still basic. Any pi systems that pull the non-bonding pair in reduce the basicity. So if you have a non-bonding pair adjacent to an aromatic ring, or you have a non-bonding pair adjacent to a double bond, those non-bonding pairs are pulled into those pi systems, and they're not completely pulled in, they're just partially pulled in, and so the basicity of that non-bonding pair is reduced. Likewise, if you are looking at the hybridization of the non-bonding pair, it will have an effect. Substituents on a benzene ring will affect the basicity. Electron withdrawing groups on a benzene ring so if you have aniline with an electron withdrawing group on it, then what happens is that electron withdrawing groups pulls the electrons away from the nitrogen, and so you reduce the basicity. Whereas if you have electron donating groups, it's pushing electrons into the pi system and therefore into the non-bonding pair, and so it increases the basicity. Alkylamines all have alkyl groups on them. They're pushing electrons onto the nitrogen, so what you have is a more basic amine when it is an alkylamine. Pi system amines, aromatic amines are all less basic than alkylamines because alkylamines have electrons being pushed into the non-bonding pairs by the alkyl groups. So go ahead and look at these and try to rate them as most basic to least basic. Okay, well, if I look at this, I will see here is benzamide. You can say that is non-basic. It's an amide, so that's non-basic. If I look at para-toluidine, that's paramethyl That's aniline with an electron donating group, and here's aniline with an electron withdrawing group, and then there's aniline. These things are going to be easy to compare to each other. Aniline's going to be in the middle. Toluidine will be a little bit more basic because it has an electron donating group, and nitroaniline will be less basic because it has an electron withdrawing group. Then benzylamine, this is an alkyl characteristic, it's not in resonance with the benzene ring. So this is an alkylamine, and so it's even more basic. So the most basic is benzylamine, and then comes toluidine, then comes aniline, then nitroaniline, and then last of all is benzamide, which is non-basic. As I said earlier, the hybridization affects the basicity of amines. The non-bonding pairs must be available and polarizable. Polarizable means that if it's polarizable, it's easily pulled and pushed. And if you have a polarizable non-bonding pair, it can be protonated more easily. So when we look at hybridization, when you have a lot of S character that pulls the non-bonding pair in closer to the nucleus, it makes it less available, basically. And the energy of the orbital decreases also, which makes the electrons less available. So anything with a more S character you have in the hybrid orbital that's holding the non-bonding pair, the less basicity you have. So let's look at the hybridization. We've got sp3, sp2, sp, and p. And if I look at sp3, that's 1/4 S. And all the way down, let's go to sp, that's 1/2 S. Here the electrons are less available. Here the electrons are more available. So if you have sp3 electrons for the non-bonding pair, it's more basic. And then as you go down, it becomes less and less and less until you get to a p orbital that's in resonance with a pi system, and that is the least basic of all. So for example, we look at pyridine. Notice this nitrogen has a non-bonding pair on it that's unwritten. 1, 2, 3 areas of electron density, so this is an sp2 nitrogen. That means its non-bonding pair is in an sp2 orbital, and so it's less basic than an alkylamine, which is sp3. You try it. Which is more basic, 2-octanamine or the imine of ammonia and 2-octanone? Well, the first thing we need to do is draw the structures. So there's 2-octanamine, and here is the imine. The non-bonding pair on the amine is in an sp3 orbital. The non-bonding pair on the imine is in an sp2 orbital with more s. So the non-bonding pair here is at a higher energy in the amine, and so it is more basic. So to summarize all this, the non-bonding pair is the key to understanding basicity. The more available it is, so high electron density on the nitrogen, more basic. Less available it is, less electron density on the nitrogen, the less basic it is. We also can look at the hybridization, and the more S that the non-bonding pair has, the lower in energy it is, and the less basic it is. Amines are also weak acids. They have protons on them that can be removed. Organometallic compounds can remove them, or alkali metals can remove them. We've used them in the past. Sodium amide is something that we've used as a strong base. Lithium diisopropyl amide, LDA, was a strong base that we used to deprotonate the alpha carbon of a carbonyl. Amides are not bases, keep that in mind. So they will not be protonated. If you try to protonate an amide, what is protonated is the oxygen, not the nitrogen. Keep that in mind.